Hi, yes, thank you. Thank you for joining Room Air Distribution Fundamentals. My name is Ryan Johnson. My title at Price is Research and Development Manager. So I manage our mock-up lab here in the U.S. side, as well as oversee our tech centers for our U.S. operations, and I'm pretty heavily involved with ASHRAE at the national level. So if you have any questions about ASHRAE and ASHRAE research in regards to room air distribution, always feel free to ask. This course is, I like to read the course descriptions aloud, and that's that the air distribution is a vital component in any building's ventilation system. When we have good air distribution, that results in quiet, comfortable, clean indoor spaces, and poor air distribution results in noise, drafts, stuffiness, and odors. So in this course, we will cover the fundamentals of air distribution. We will explore what industry standard terms exist and what definitions exist used to describe air motion, as well as any other relevant codes and standards and important design considerations. We'll first cover just the basics of air distribution. We'll look at some smoke videos and see how does air actually travel within a room. We'll cover the basic terminology used to describe that, so we're all using the same language, and then we will cover the some significant standards that discuss and define what is good air distribution, what is bad air distribution. So the videos we'll show here are from our flow visualization room in Atlanta. So this is just a theatrical smoke. It's kind of like a fog machine you'd see at a concert, but we put it in the ductwork and use that to visualize how the air moves throughout the space. What we're seeing here is a standard square plaque diffuser, and it's used in what we call a mixed air system. So the air is being discharged at the ceiling, typically at a high velocity at whatever design CFM we need, moves across the ceiling, and then fills out the rest of the room. There's several different diffusers that exist, many different models, all have different performance parameters. Typically speaking, we would supply our air at about 55 degrees Fahrenheit, though sometimes if we need to heat the room, we might supply the air at a warmer temperature, usually around 85 degrees Fahrenheit. If we need to, we'll have a thermostat within the room, and in order to modulate the room temperature to match what the thermostat requires, we will often control not necessarily the temperature of the supply air, but we will instead adjust the volume of the supply air. So in this video, it almost looks like it's in slow motion. That's not the case. We're just supplying less airflow. If a room needs to be cooler, we will increase the volume of our supply air, so thus bringing more of that 55-degree air into the space. And if the room needs to warm up, we can close off a damper and supply less air. That supply air would still likely be 55 degrees, but since there's less of it, the room loads within the space will essentially overpower and allow the room temperature to slightly increase. Here's a larger view of what's actually happening. So we'll go through this step by step. We have our air that enters the space from our air outlet, whether usually a ceiling diffuser such as this. The neck velocity at the air outlet can be anywhere between maybe 300 and up to 1,000 feet per minute. The higher the neck velocity, the longer the further the air will travel, but also the more noise that it will generate. As the air travels across the ceiling, it will then eventually come to a wall or some boundary. And we'd like to place our diffuser such that by the time the air enters what we call the occupied zone, or roughly 6 feet above the floor, it is slowed down enough to reach about 50 feet per minute. 50 feet per minute is a rule of thumb velocity that we use, because once you're below 50 feet per minute, the air is slow enough that you typically won't have a draft, and it is also warmed up to room temperature at that point. This way we're mixing air throughout the space, but it's not creating a draft, it's not noticeable to the occupants. The air will then continue to mix throughout the room. We see in this video that there is air moving inside the occupied zone, but it is slow enough that our occupants would not perceive it. There's not a whole lot of discernible pattern at this point, and that's okay. For a mixed air system, we're usually not trying to create a very specific air motion. We're just mixing all the air, and it all becomes turbulent within the space, and there is no discernible pattern. Now, eventually, there is, since we do have a high velocity airstream at the ceiling and a relatively low velocity within the room, that will create this air entrainment effect, where the air does eventually induce upwards and then recirculate back into that supply air jet. And you can almost see like this curving arc motion. It's not a motion that we can readily predict, but this is the general trend of the air motion within the space for a mixed air system. It will induce back into that supply air jet, recirculate, and create our mixing action. It can also be in our advantage to supply air directly onto exterior wall surfaces, especially windows, any place that has a warmer or colder surface temperature. When we have warmer, cold surfaces, those can create thermal radiation effects, which will be uncomfortable for occupants. And if a surface is too cold, it can create condensation, which is moisture, and can lead to moisture damage if left untreated. Supplying air directly onto those surfaces helps normalize that surface temperature such that our occupants no longer perceive the radiation, and it removes the risk of condensation. An alternative room air distribution method is what we call a stratified system. In this case, this is a displacement diffuser. This is functioning differently than what we saw previously. This is a low velocity system. We're not forcing the air into the space, but instead it's actually supplying this cool air, almost like dumping it like a bucket of water. It's dumping this cool air onto the floor of the room. Then our occupants, which are simulated by these white cylinders in this video, our occupants, whether it's ourselves or if you have electronic equipment or any other heat load within the space, we are generating heat that is warming the air around us, and warmer air is more buoyant and thus must rise. So in a displacement system, this takes advantage of that effect, causing all of our cool air to be at the floor and then all of our warmer contaminated air to rise up to the ceiling. This effectively creates a heat-seeking effect of our supply air directly to our occupants. We can see this here's a larger view of the same effect. So say this is the same room with a single displacement diffuser. We have our 3 occupants. Each of these are outputting roughly the same sensible load as an adult male, and our air will gravitate towards them because it must. The heat loads within the space do drive air motion, and if they are the only thing driving the air motion, then the air must gravitate towards them. There are no fans within these cylinders. It's simply, in this case, these are just incandescent light bulbs within the cylinders, and the heat is driving the air upwards. Heat sources are typically also contaminant sources. So in a stratified system such as this, it's essentially taking all of our contaminants at the source and driving them up to the ceiling. Now we'll cover some common terms. In those videos, I probably use some terms you may or may not be familiar with, such as throw or occupied zone or sensible load. So I like to cover each of these one by one just to keep us all on the same page. So throw, this is a term that we use to denote the distance the air travels before it reduces to a specific velocity. We'll never say how far, we can never describe how far the air travels before it stops, because technically the air will never stop. As long as there is a heat load in the room or some type of supply air jet within the room, that will always drive continuous air motion, and the air will never effectively reach 0 feet per minute. However, we can describe how far the air travels before it slows down to a specific velocity. We can reliably do this up to about 50 feet per minute before other factors within the room would start affecting the room air motion. This boundary we call the isovel, where if you break down your, I guess your Greek here, that'd be isolated velocity. That is a boundary of uniform velocity. For each diffuser, we would generate isovels similar to this, and this denotes the pattern of the air motion. We will always find that the isovels for higher velocities have thus a shorter throw distance than the isovels for lower velocities. The air will only slow down. We won't have any air jets that accelerate once they enter the room. You'll find the throw distances in manufacturer catalog data from any manufacturer. This is actually an ASHRAE Standard method to gather this data, and we will typically describe it in terms of distance to 150, 100, and 50 feet per minute. And then the numbers outlined, if you're in the US, will be in feet. If you're in Canada or another country that uses metric, that will be usually in meters. Now, the actual throw distance is not super uniform. I like to add this slide. This is from a mock-up we did in Atlanta for essentially this is a slot diffuser that we mounted at waist height for this specific project. It threw air across the room and we measured the velocity throughout the whole room and see how it affected it. And we can see our isovels for 150, 100, and 50 feet per minute. But you'll notice that 50 feet per minute isovel is a lot, it's not as well defined. And that's because 50 is really pushing at the boundary to the point when other factors within the room, whether it be occupants or just someone walking across the room, can affect that 50 feet per minute isovel. It's pretty fragile. We'll even see some points here where the velocity dropped to 45 and then went back up to 55. That's just due to turbulence of the airstream. That's very normal. I bring this up just to mention that when you look at catalog data and it says the throw distance to 50 feet per minute is 20 feet, it might actually be 18 feet. It might be 22 feet. It might be a little less. It might be a little more, and that's okay. That's not a game breaker. That's not going to be the difference between someone having, the room being stagnant versus a room being super turbulent. We also have this term called drop. This is technically describes the height that the air descends before achieving its throw distance. If we have a isolated jet, like in this cross-sectional view here, it won't usually travel in a straight horizontal line unless it's completely isothermal. If we're supplying cool air, it is denser and will have a tendency to kind of drop into the room. There is also the effect that an air jet will simply expand, and that can also cause it to descend into the room. We also colloquially use the term drop to describe an air jet that maybe disconnects from the ceiling, whether from an obstruction or maybe it's focused downwards a bit. Sometimes we'll have air jets that drop from the ceiling and enter the occupied zone prematurely, and that's simply the term we use to describe that. The occupied zone, this is another general term we use to describe the actual space within a room that we would expect occupants to be inside. This controls which space we thus want to make comfortable. It's generally described as 6 feet above the floor and 1 foot off of adjacent walls. You would also, if you look at ASHRAE standards, it's typically also 3 feet off of exterior walls. Outside of this boundary, we just generally wouldn't expect occupants to be there long term. Very rarely do people stand flush against a wall, and unless someone's on a ladder, rarely are they standing long term above 6 feet above the floor. We like to size and place our diffusers such that we reach that 50 feet per minute throw isovel at the boundary to the occupied zone. By the time that the air is slowed down to 50 feet per minute, it's also warmed up to room temperature. Now, warming up might not be technically the correct term. It's actually entraining a lot of room air motion within to the air jet, such that by the time the air has had enough friction with the rest of the room air, it's entrained enough room air to be effectively room temperature at this point. This means that the air is slow enough and warm enough that it is imperceptible to the occupant. And we would size our throw distance to be the sum of the horizontal plus the vertical distance to reach the occupied zone. So if our air, if say maybe we're 10 feet away from an adjacent wall, but maybe we have a really high ceiling and we have another 10 feet, we have to travel vertically downwards to reach the occupied zone, our total throw distance would need to be about 20 feet then. Now there's an effect called the Coanda effect. So this is actually originally derived back in aerospace engineering to describe air flowing around a wing of a jet, essentially an airfoil. But we work in HVAC. We get to use aerospace principles every so often ourselves. And the Coanda effect is essentially a term to describe the tendency for high velocity air to cling to solid surfaces. This gets into boundary layer theory if you want to look into the engineering, where high velocity air is, essentially, it's sticky. It likes to stick to solid surfaces, and that means that there's a less boundary of the air jet that's exposed to the rest of the room, and thus less friction between the air jet and the otherwise low velocity air. With that less friction, that allows the air to travel further. In fact, as a rule of thumb, this is a simplification, but we would say if you don't have an adjacent surface, then your throw distance reduces by about 30%. Our catalog data is measured assuming an adjacent surface, whether it's a ceiling or a sidewall, and so it assumes the Coanda effect is in place. If you are using an exposed application, you would expect the throw distance to be about 30% less than what the hard catalog book tells you. Now, in terms of actually getting the data of our diffusers, a diffuser itself is a fixed geometry. So if we have some known pressure upstream, which is going to be some component of static and velocity pressure, if we have a known velocity pressure, that will result in some required upstream static pressure and some resultant flow rate, throw distance, and noise generation. It must be, because the diffuser is constant and we're simply putting air in, and then air must come out the other side. And this is how we tabulate our catalog data. So if you're new to catalog data for diffusers, it's kind of a lot of information to look at all at once. Sometimes you just have to stare at it for a while for it to click. But to guide you through what we're looking at, we, generally speaking, for a grill or diffuser, we would have some neck size or some area size. So in this case, on the y-axis, we have the size of the neck, whether it's a 6-inch neck or an 8-inch neck or a 10-inch neck on the back pan. And then given that diffuser and that neck size, for some known neck velocity, we will have some known pressure drop, and that will result in a specific flow rate and a specific noise generation and a specific throw distance. It must, because at that point, all the variables are constant. As our neck velocity goes up, we will see more airflow, because velocity times area equals CFM, or volumetric flow rate. We will see more noise, because as we have higher velocities in our system, that creates more friction in the air streams and will create more noise. And we will typically see more throw distance as well. And that makes sense, because higher velocity at the diffuser results in a higher velocity air jet, and the air travels further into the room. Now we'll look at some important ASHRAE standards that guide us towards using our diffusers in a way that promotes a comfortable, well-ventilated environment. The first we'll look at is ASHRAE Standard 55. This is designing for thermal comfort, and it goes into all of the details you would need to know that kind of correlate between air movement, temperature, and human physiology. How do we as occupants relate to the environment around us, and what results in a thermally comfortable environment? ASHRAE 55 describes thermal comfort as a function of 6 primary variables, as our metabolic rate, how much clothing we're wearing, the actual air temperature of the space we're in, the radiant temperature, which is slightly different, the air velocity around us, and the humidity of the air. And we'll go through each of these in a little more detail. Now, temperature, I like to slow down and actually define what is temperature. If you, depending on what your background is, or if you study a specific field of engineering, each type of engineer, I feel like, kind of focuses on different types of temperatures. And if you ever open up like an HVAC engineering handbook, it can often describe maybe 5 or 6 or 7 different temperatures. There's dry bulb, wet bulb. You might have standard effective temperature, effective draft temperature, radiant temperature, and it can be kind of hard to figure out what do they actually mean. They all get jumbled together. Dry bulb temperature, this is our most common one. This is the temperature of the air indicated by any ordinary thermometer. If you want to go into the science of it, it's a direct measurement of the kinetic energy of the molecules of the air itself. And it's exactly how it's described. It's a thermometer, it's just a bulb that's dry, that's exposed to the airstream. Now, wet bulb temperature can get a little more confusing. If you Google wet bulb temperature, you'll get a definition similar to what's shown here on the screen. It's the temperature through evaporation that can bring moist air to saturation adiabatically. That is technically true, but it's like, okay, what does that mean? I think I know most of these words, but put them together, it's kind of confusing. And really, it's just a thermometer. It's technically a dry bulb thermometer with a wet cloth around it. So if we take any typical thermometer and put a wet sock around it, it will reduce the temperature it measures based on the humidity of the air around it, because that wet cloth is evaporating, and that is an endothermic process, and that is drawing heat away from the thermometer, and that is reducing the temperature measured. The anecdote I like to use to describe wet bulb temperature is, say it's a summer day and you're out at the beach, or say you're out at a pool, and maybe it's really hot outside and you feel warm, and then you jump into the pool and you get out of the pool, and now you actually feel really cold because you have all this water on you. And what you're experiencing at that point is actually the wet bulb temperature, because now you have all this water on your skin, it's evaporating, that's drawing heat from your body, and that makes you feel colder. It's the same exact effect of how we would measure wet bulb temperature. And if you have a very humid environment, say it's 100% humidity outside, in which case wet bulb temperature equals dry bulb temperature, then you won't feel a difference thermal comfort-wise between having dry skin or having skin covered in water. Radiant temperature, this is another one that can sometimes be overly technical. If you look for a definition, it'll tell you the temperature of an imaginary enclosed surface that would create an equivalent radiant heat transfer as the actual room. A little confusing. What does that mean? That simply means it is what a thermometer reads, what any typical dry bulb thermometer would read if it's enclosed in a highly absorptive, highly emissive device, such as this copper globe. Thermal radiation is affected by, well, lots of things. You probably might remember like the shape factor functions from engineering textbooks. It's also dependent on the absorptiveness and the emissivity of a given surface. A copper globe that's painted a matte black like this is highly absorptive and highly emissive, and thus will absorb the maximum amount of thermal radiation it can from the environments around it. How would we apply this? Well, we can, let's take an example. Here's a nice little diagram showing an occupant in a room with lots of surfaces, and each surface might have a slightly different temperature. So we might have a dry bulb temperature in the room of 72, but maybe it's cold outside, the window temperature is 50, maybe the floor, maybe it's a radiant floor, it's a little bit warmer. Our interior walls are closer to room temperature. Maybe there's some electronic equipment that's generating heat. Maybe we still have high temperature light fixtures at the ceiling. And all these together are either emitting thermal radiation or absorbing thermal radiation from the occupant, in which case they might ultimately feel what would be measured as a radiant temperature of, let's say, 76 Fahrenheit. So it's usually a little bit warmer than the dry bulb. Now, there's some interesting things that happen with thermal radiation. First is it is a directional effect. So if you have say a really cold window in one direction, maybe at that moment, at that place where you're standing, the dry bulb temperature could be comfortable and the measured radiant temperature could be comfortable. But just because you have a cold surface from one direction that is absorbing heat from you from one direction, that asymmetry can trigger a discomfort response in our brains. It might be subconscious, but it can happen. And that effect differs depending on whether it's a warm or a cold surface or whether or not it's a wall or a ceiling. This graph is pulled directly from ASHRAE 55, showing that. So if we are designing a space and we expect maybe an exterior wall to be warmer or colder than normal, or maybe a ceiling to be warmer or colder than normal, maybe this is part of the design, or maybe there's limitations in the application that we can't get around that should trigger in our mind, wait a second, if I have a surface that's warmer than normal, that might trigger a discomfort response. Let me look at this chart. Okay, let's figure out what that temperature might be. If we're within this bounds, we should be okay. The same goes for a floor. If you have a floor temperature that is significantly warmer or significantly colder, that will also trigger a discomfort response. For design purposes, that might affect if you're doing, say, a thermally radiant floor, which can be a very effective design. If you design that floor to be too warm, that will trigger a discomfort response. But also, if you have a cold floor, say like a concrete slab, maybe, I don't know if any of you live in a house with a basement that's unconditioned. If you've ever felt that cold basement floor in the winter, it just feels like the heat is being sucked out of your feet. That's the same effect. There's a radiant effect happening there. Now, I'll introduce one more temperature. This is called the operative temperature, and this is what the room feels like. In general, this is calculated as the average between that radiant and the dry bulb temperature. So in our previous example, if we had 76 and 72, our operative temperature would be 74. And in ASHRAE 55, there are lots of models that exist to predict how comfortable a room will be. And for those models, they almost always use the operative temperature. So we'll want to know the radiant and the dry bulb component in order to predict how comfortable a space will be ahead of time. So some other fun, cool tips, as I like to say, there is a limit to vertical air temperature difference. If we are designing, say, a stratified system, they are we get the most benefit from a air change effectiveness and a energy consumption side by maximizing our stratification. We actually want there to be vertical air stratification in a displacement system or in an underfloor system as well. However, there are limits that we can push this. As of the current writing of 55, it allows up to a 7.2 degrees Fahrenheit difference from ankle to head for an occupant who's standing. This is pretty significant. Our stratified systems aren't going to push this high. If you start pushing upwards to a 10-degree difference from foot to head, that's when you start getting uncomfortable. We've simulated this in our mock-up lab in Atlanta, and it's certainly an eerie feeling once you start pushing 10 or 12 degrees Fahrenheit stratification. It's not an effect that happens in nature, but as long as we stay with under 7.2, we'll be good. We'll be comfy. There's also standardized limits of cycles and drifts within our temperature throughout the room. So in any HVAC system, there is some control operation. We might just be turning the heat on or off in a binary fashion. There might be a more analog control. But in any control system, it's rarely going to hold flat at steady state. We're going to cycle up and down around our temperature set point. That's okay, that's normal, But if that temperature cycles too quickly or at too high of a magnitude, that will trigger a discomfort response in our heads. The amount the air is able to fluctuate in temperature depends on the amount of time that it's fluctuating based on these limits presented here. So even say, for example, in this time period, 1/4 of an hour, the temperature can fluctuate by 2 degrees Fahrenheit. If you have a system where it's fluctuating by 3 degrees Fahrenheit, even if that minimum and maximum in isolation are probably maybe comfortable temperatures, just the fact that that temperature is fluctuating that quickly can start to trigger a response. And even if you have a system that's fluctuating that quickly, you're probably also getting a lot of noise issues because you've got your air turning on and off at these high magnitudes. That might discomfort a noise complaint as well. All right, so we've got some rules of thumb. In general, we want our operative temperature to be between 73 and 77 Fahrenheit. That might seem a little high, but keep in mind that takes into account the radiant effect, which is usually going to make skew warmer. We want our relative humidity to be between 30 and 60%. Less than 30% is not necessarily bad from a thermal comfort perspective, but it can create dry eyes, dry noses. It can create other discomfort. And we generally want our air velocity to be less than 50 feet per minute in the occupied zone. One point of note is personal control. Some studies have shown that if you give an occupant control of their own environment, they will be more accepting of the resultant environment. So if you have a single office room and maybe with a single occupant and they have their own thermostat, that will make them happier with the environment, assuming that their thermostatic control actually works. The way I like to think of it is, when we're driving our cars, we have our air conditioning in the car, and sometimes you just want it to be really warm, or sometimes you just want the AC on full blast, and whatever you choose might not fall within what ASHRAE Standard 55 would recommend, but it's your choice, and since it's what you want to do, you're comfortable with it. That's effectively what's happening. Now, metabolic rate, this affects our perception of the temperature around us as well. This is simply the amount of heat that we generate within our bodies. That's our metabolic rate. We consume food, and some portion of the calories that we burn is just our body's metabolism, and that ultimately outputs as heat to the environment around us. There is a unit for this. This is what ASHRAE denotes as a MET. So effectively about 100 watts or 350 BTUs per hour. Someone that's just sitting at a computer screen, so maybe you right now, is probably outputting about 1 MET. Someone who's walking around could output about 2 METs. If you're doing basic exercise, going for a jog, that can fluctuate between maybe 3 and 7. And someone outputting as much effort as they possibly can will output upwards of 10 METs. In fact, so it varies widely, but for the most part, if someone is outputting 4, 5, 6, 7, 10 METs, they are likely engaging in an activity where they are less concerned about the thermal comfort around them. So we typically don't design for someone at 10 METs, we design for someone at 1 METs who's trying to work, who is otherwise not moving. There's also units of clo for clothes. It's a real thing. And this is, if you go through ASHRAE standards, they actually have charts and tables denoting effectively an insulation value for different articles of clothing. If we want to be scientific, this is actually kind of the way you have to do it. And depending on whether it's in the summer or during the winter, we will be wearing different amounts of layers of clothes, and that will result in different amounts of insulation from the environment around us, and thus what temperature we are willing to accept. Now, ASHRAE 55 has a handful of different methods for denoting, for predicting thermal comfort. I won't go through all of them in this presentation, but one I like to highlight is what's called the analytical method. And you can actually use this one at home. What I have linked here is a thermal comfort tool from UC Berkeley, and it allows you to input all of our primary thermal comfort parameters, such as temperature, airspeed, humidity, metabolic rate, and clothing. And from there, it will actually generate a psychometric chart based on your environment and tell you how close you are to the sliver in the middle that would be considered comfortable. When I give this presentation to, pre-COVID, when we would have larger groups, maybe 40 or 50 engineers in the room, we'd pull up this thermal comfort tool. I kind of give a poll. I'd ask the occupants, hey, who feels a little warm? Who feels a little cool? And for the most part, then we would type in the parameters of the room into this thermal comfort tool, and it would spit out some predicted percentage of people who would be dissatisfied with the environment. And for the most part, we'd actually usually be within 10 or 15% of what the tool would predict. So it's never going to be perfectly accurate, but it uses all the modern research and polling and that's existed over multiple decades, and puts it all together and spits out a number that is a best prediction based on the data available. We'll look at ASHRAE 62.1. So ASHRAE 62.1, this is the standard on indoor air quality. So this is no longer about thermal comfort, but more about the quality of the air itself. We, as as occupants, we spend about 90% of our time indoors, and thus we're pretty dependent on the cleanliness of the air of our ventilation system. Compared to the outdoors, we are far more exposed to pollen and dust and bacteria that doesn't necessarily exist in the fresh air that we would find outdoors. There's also a lot of unique pollutants from, say, like building materials and chemicals of furniture or other equipment within a room that you won't find outdoors. This can result in all sorts of common ailments and common symptoms from a poorly ventilated space. These are just a handful of common ones that we need to be wary of indoors. This is just pulled from ASHRAE handbook. A lot of these, especially those of you familiar with, say, like Legionnaire's disease, that's an illness that comes up from sitting water that is unique to building plumbing systems and the way we store water. The poorer and poorer ventilation we have, the more and more vulnerable we are to these unique symptoms. Now, humidity plays a big role in this. If we have lower humidity in a space, that's, again, not inherently a bad thing. In fact, depending on your region, those who are closer, those on the West Coast will often have very low humidities outdoors and thus lower humidities indoors. That will result in drier nose, drier eyes. It can result in a longer airborne time for any airborne viruses, and that's because there's less water molecules for them to latch onto, makes them more buoyant and makes them sit in the air longer. Higher humidity is a much larger concern because once we have higher humidity, that results in condensation, that results in moisture damage indoors. And water damage is difficult to treat. Once you start having mold and fungus and bacteria growth, that results in physical damage to our infrastructure that becomes very costly. It grows very quickly once it's there and can result in all sorts of health risks for our occupants. So we definitely want to be below 60% humidity. 40 to 60% is generally always ideal. 62.1 gives us an equation for our minimum ventilation requirement for an indoor space. Denoted by this equation here, it's going to be a function of the amount of people we expect to be indoors and the size of the space, as well as the type of the space. So given this equation, we have our VBC, that's, our volume of air to enter the breathing zone, equals a function of our number of people times the type of space plus the amount of area times the type of space. And those RP and RA values are given in table form. Some spaces require more air intuitively. So if we have a classroom or daycare, especially if we have a critical environment such as any space in a hospital, those are going to require much higher ventilation rates based on the number of people and space. Now, we also want to consider our ventilation effectiveness, because just because we are maybe pumping in a certain CFM of air into our room does not necessarily mean it's ventilating the space properly. You can put 1,000 CFM into a small room, but if it's the wrong diffuser in the wrong location with the wrong temperatures, it's possible very little of that air will actually reach our occupant. We describe this based on what we call the ventilation effectiveness. That's this EZ term. And it's calculated, you can actually test for this, it's calculated by the amount of contaminants in our return relative to the amount of contaminants in the room. So, for example, if we have maybe slightly more contaminants in our return, in this case, maybe this is carbon dioxide, CO2, maybe we have 1,025 ppm in our return and 1,000 ppm in the room, those are about the same. Our ventilation effectiveness is, in this case, 1.05. This is actually a ventilation effectiveness of 1.05 is pretty normal. So in our standard mixed air system, such as what we saw in those smoke videos before, we would actually expect a ventilation effectiveness roughly at 1.0. It's very common. It's actually what it ends up being. That means that the air in our return is just as clean as the air in our room, or vice versa. You could say the air in our room is just as dirty as the air in the return. They're the same because it's well mixed. They must be the same. Now, sometimes if we have a poorly placed diffuser and it's short-circuiting some of that supply air directly into the return, that can reduce our ventilation effectiveness and actually make our return cleaner than the rest of the room, resulting in a ventilation effectiveness less than 1. Or if we're supplying warm air, we know that warm air is more buoyant. It likes to hug the ceiling. And actually, according to ASHRAE Standard 62, we would expect a ventilation effectiveness of closer to 0.8. And as that temperature gets warmer and warmer, that ventilation effectiveness goes lower and lower. Now, one way to fix that is if we have a low wall return, that brings the ventilation effectiveness back up to 1, because now that warm air, even though it might want to hug the ceiling, it still has to travel through the occupied zone before it can escape the room. Sometimes we get the question, especially this last year, does an HVAC system spread viruses? And in the sense, in a mixed air system, we are mixing the air around us. And so if there is some contaminant within the room, it will by design mix throughout the room. But it does a lot more in general to help, because we are diluting the air within the space. So if we have some source of contaminants within a room, maybe in one corner, if there is no ventilation in the space, that corner would have a very high concentration of contaminants. But by creating a ventilation system, we're able to dilute it such that it's, although it might be mixing throughout the room, it's at such a lower concentration that it is, in general, far less potent than otherwise. I like to say that a minimum amount of ventilation is way better than no ventilation, and if we can engineer it more, that's even better than that. We want to check for humidity, we want to check for stagnant zones, and always want to check for proper filtration and outdoor air requirement. Finally, we'll look at ASHRAE Standard 70. This is the test standard that describes the how we actually get the performance data for grills, registers, and diffusers. This is done in a laboratory setting. It must be, because as we know out in the field, out in an actual construction site, there are 1,000 variables to consider, and usually maybe we can define 900 of those variables, but there's still 100 that are probably outside of our control. And so the results of what you get in the field from a diffuser might not match what you get in the catalog. ASHRAE Standard 70 actually assumes you have 3 duct diameters of straight duct right behind a diffuser backpan. You probably don't get that a lot in real life. You probably have a short plenum, you probably have an elbow or something narrower than that behind your diffuser. That's not bad, but it might affect what you get from the catalog. So what I like to show are a few examples of how that changes the product. Here's a couple of examples I've found from my own travels of diffusers following this advice. So sometimes it's at the expense of the architecture, where you can get your 3 duct diameters, but it might not always look good. Sometimes if you have a large ceiling, you can afford the space, such as the picture on the right, where we do get 3 duct diameters. Now, granted, I don't know. Personally, I don't think this louvered face diffuser exposed in the ceiling like this looks great, but it is probably performing as expected. When we introduce an elbow, the air, even if it has a uniform velocity profile upstream, when it comes around that curve, it likes to hug the outside of that curve. And when we come out of the elbow, we no longer have a uniform air velocity. We're going to have a higher velocity on one side relative to the other. This affects how the air leaves the diffuser. So here is our throw profile, that isovel for this modular core diffuser with our ASHRAE Standard 70 conditions. Once we introduce a hard elbow, that throw pattern kind of shifts. Not a big deal. In fact, if you were to do this in a lab or go to your work site with an anemometer and check the ceiling, it would probably be hard to even measure how different it is from the catalog. It's just a little skewed, maybe a foot or 2 longer in one direction than the other, but not a big deal. Your room's going to be fine. Once we start introducing flex duct, and this is showing really a worst case scenario, now things get tricky. In this case, we have such a tight elbow, and frankly, just a lot of pressure drop and noise generation in that flex, that now our air is no longer throwing in one of those directions. We can end up having, I like to say as a rule of thumb, maybe plus 30% of air in one direction and at least minus 30% of air in the other. Though it can be worse, it can be better than that. It's just very hard to predict. Now, this is for, again, this isn't going to say that all flex duct does this, but if you're using flex duct, we really recommend you have some structure to it that has a large enough radius in the bend. And if you can, use one of those kind of, one of those devices that kind of structure the elbow. That way it doesn't create a tight 90-degree bend, but a longer radius. Now, a square plaque diffuser, and this would work for square cone diffuser as well. Any diffuser has a radial throw pattern like this is generally less affected by these inlet conditions. So we still will get some skewing of our throw pattern, but for the most part, it's really hard to mess these up. The air is still going to mix into the space. We still have a high velocity air jet that is hitting what is effectively just a flat plate, and it will just move horizontally. You will get very robust, very consistent performance from these products. So that concludes this presentation. For more information on all of these subjects, I would recommend you look at ASHRAE Standards 55, 62.1, and 70. There's also, within these standards, as well as the ASHRAE handbook, you can find more terminology to describe air motion. And I hope this presentation has been informative to give you the foundations to move forward with your designs. For any more information, you can also reach out to the Price team based on product group at the email addresses below, as well as the Price Engineering Handbook. From there, that concludes this presentation, and I thank you for listening in.